Hello everyone, my name is Ghodsi EKOP and I'm a second year PhD student. Today I want to explain how we measure the universe using radio astronomy, and more specifically I will focus on the theta Z method. Okay, let's start with the big question. Why do we need to measure distances in the universe? Well, the oldest and most fundamental question in the history of humankind is why we are here and what happened in the universe and what will happen in the future. To answer to this question, first we need to measure the distances to different celestial objects. Why? Because distance measurements help us to understand the structure of the universe and the evolution of the universe with time. In the right, you can see the Hubble Ultra Deep Field, which shows a small section of space in the southern hemisphere and Fornax constellation, which contains approximately 10,000 galaxies, not a star, galaxies. Okay, astronomers use two key tools to measure cosmic distances. The first one is this one, standard candles. These are objects that we believe, at least we think that we are completely aware of their intrinsic brightness, and it's very well known. So by comparing their apparent brightness, we can determine how far they are. One of the most famous candidates of the standard candles are type 1a supernovae. The second tool is the standard rulers. These are objects that with a known physical size. So we believe that we are aware of their size. So by measuring their angular size, we can infer this time their distances. Today we will focus on the second one, this method, something like standard rulers. Okay, let's start with a little bit of history. The concept of using radio galaxies as a standard rulers was first proposed by Fred Hoyle in 1959. That he suggested that extragalactic radio sources, particularly those that they have a very well-defined structure, like this image here, Cygnus A, that you can see here in the right, they can serve as a standard rulers. Hoyles believed that if we could observe similar radio galaxies at different redshifts, the apparent angular size would give us some information we could distinguish between different cosmological models. The theta Z test is a method that tests how angular size of radio sources change with redshift, with Z here. And theoretically, we measure how this size evolves across different redshifts, and we can test cosmological models because of this one, and we can test the expansion of the universe also. But here we have some free parameters also that we need to estimate them with data later. I will explain them. But in the 1970s, the first practical attempt, they tried to apply the theta Z tests were made using data from the VLA, very large array with arc-second level resolution. Here you can see a list of early studies, and what they found that giant radio galaxies were not suitable as a standard rulers. Why? Because the structure were too diverse. We prefer something with a better, well-known structure. So what happened next? A shift in approach happened actually. So this time researchers focused on the compact jet structure of active galactic nuclei, or AGN, instead of previous method, because they are more stable and it's easier to compare across the different redshifts. So what was the conclusion? Like here you can see some studies that list. What was the conclusion of this finally? First, they suggested if we use jet structures in AGN from VLBI dataset with a milli-arc-second resolution, we can reach to a better constraint. And furthermore, they mentioned that, because you can see here, it's like just a few hundred of them. So they said that in future, with thousands of data instead of a few hundred of them, we can reach to a better constraint. And now we are there in the future after almost 25 years with thousands of data. Okay, I said VLBI, but what exactly is VLBI and how does it work? You can see here in the left. Imagine that you have two radio telescopes located in two different places on the Earth. For example, let's say one of them in Europe and the other one in the US. When a distant astronomical radio source emits signals, both telescopes receive the signal, but at a slightly different times because of their separation and their location. VLBI synchronize this signal by using extremely precise and accurate atomic clock, and then the data from both telescopes combined, and it can mimic like a big telescope with a very wide baseline, which we call them the baseline. So the longer the baseline, the better the resolution. And these two different sides of the Earth can be the longest kind of baseline we can reach. Okay, to use a theta Z test as a cosmological tool, our current approach involves using advanced statistical methods like Markov chain Monte Carlo or MCMC to analyze agent properties and improve our ability to constrain cosmological parameters. The first primary result or preliminary result that you can see here in the left shows that using MCMC method, we can constrain three astrophysical parameters. Just as a reminder, you can see these parameters here again with a red circle. Two of them, n and beta, are dimensionless, and L has a dimension of parsec. But besides this, we want to constrain cosmological parameters like the matter density parameter omega m or the Hubble constant h0. But this is also including challenges, which I am going to mention in the next slide. Okay, by adding cosmology so far, we had some challenges, which the most important one is coming from the dispersion of the data. As you can see here in the left, this is the this is the theta Z plot, which green dots coming from data, and these curves in different colors showing prediction based on theory and again based on different cosmological parameters. You can also see beam data in red, and what we are working on it right now is to reduce this dispersion by using, for example, different methods like sigma clipping. And this is what we are currently trying to further verify with simulation also, as you can see in the right panel. To sum up, to understand cosmic evolution, we need to measure distances. And standard candles and standard rulers are two main approaches or two main key methods to measuring distances. The theta Z test also uses can be something like standard ruler, and it uses the angular size of a radio galaxy to test cosmological models. Early attempts faced challenges, but VLBI has kind of revolutionized the method by providing high-resolution observation. And our ongoing research and future surveys will further refine our knowledge of cosmic expansion. Thanks.